Hello everyone. Today we are going to start the lecture on simply supported beams. First we will see some standard cases, then we will do some numericals. First we are going to analyze a simply supported beam. When the simply supported beam carries a point load in the center, let us keep the span of the beam as L. Let us keep the left end as A, the right end as B and the center as C. First we have to find the vertical reactions RA and RB. This beam is symmetrically loaded, so RA and RB will be the load W upon 2. Only there are two reactions we have to find because in the simply supported ends there will be no movement. Using the right hand side rule, we can find the shear force values at just left of A, at just right of A and at just left of C. At just left of A, the shear force will be 0 and at just right of A, it will be RA which is acting upwards, so it will be positive. Let us find the shear force at just left of C. Up to the left of C, we have only this. So here also the shear force will be the same W upon 2. To find the shear force values at just right of B, at just left of B and at just right of C, we can use left hand side rule. At just right of B, the shear force will be 0 and at just left of B, we have RB which is acting upwards, so it will be negative. Let us find the shear force at just right of C. Up to just right of C, we have only this, so the shear force will be the same minus W upon 2. In all of these 3 points, we are finding the shear force at just left and at just right because in A and B we have vertical reaction and at C we have a point load. Here you can see the shear force diagram. In all of the points we have two values. At just left of A it is 0, at just right of A it is W upon 2. In the point C there are two values. At just left of C it is W upon 2. And at just right of C it is minus W upon 2. At B also there are two values. At just left of B it is minus W upon 2 and at just right of B it is 0. Then we can connect all the points so that we will get the shear force diagram. Let us find the bending moment values. We know that in the simply supported ends the moment will be 0. Let us find the bending moment at C from the point A. In this case, we have to follow right hand side rule. Clockwise will be positive and anti-clockwise will be negative. Up to the point C, we have only this. This reaction is acting in the clockwise direction, so it will be positive and the distance up to the point C is L upon 2. So W upon 2 into L upon 2, we will get WL upon 4. Here you can see the bending moment diagram. In the points A and B, the moment is 0 and in the center it is WL upon 4. Using these points, we can make this diagram. The diagram is in the shape of a triangle. Using the moment area method, we can make the expressions for the slope and deflection in this beam. For that, we have to separate the triangle by this line so that we will get two different triangles. To find the slope, this is the formula area upon EI. We have to select any one of the triangle and find the area. You can see that both of the triangles are same. So the expressions for theta A and theta B will be same. Let us take this triangle and find the area. We know the area of a triangle half into BH. Here the breadth is L upon 2 and the height is WL upon 4. So this is the area. In this way, for theta A and theta B, we will get WL square upon 16 EI. Using this formula, we can find the deflection. In the points A and B, there are vertical supports. So the deflection in these 2 points will be 0. Let us find the deflection in the point C. Let us take this triangle. In the previous step, we have found the area. Now we need to find the centroid distance. For this triangle, the centroid distance to this end is 2 upon 3 into breadth. Here the breadth is L upon 2. So it is 2 upon 3 into L upon 2. In this way, for the deflection at C, we will get WL cube upon 48 EI. Alternatively, using the Macaulay's method, we can find the slope and deflection at any point of this beam. In this beam, there are two different parts, AC and CB. So we have to make two sections, one in AC and one in CB. You can see that I have made two sections. This section at a distance of x from the point A and this section at a distance of x from the point B. We need to find the moments about the sections. We know that this beam has symmetrical loading because this point load is acting in the center. In this case, the slope and deflection values will be same from the point A to the point C and from the point B to the point C. So there is no need to follow both of the sections. We can take any one of the section because on both the sides the values will be same. I am going to select this section. I am going to find the moment about this section from the point A. In this case, I have to follow right hand side rule. Up to the section we have only this RA. It is acting in the clockwise direction, so it is positive and the distance is x. We can equate the moment to EI d square y upon dx square. We have to integrate on both of the sides. When we integrate this, we will get dy upon dx. Using this formula, we can integrate x. We will get x square upon 2. C1 is the constant. 2 into 2, it will be 4. One more time, we have to integrate on both of the sides. When we integrate this, we will get y. When we integrate x square, it will be x cube upon 3. In this term, there is no x, so we have to multiply with the x. C2 is the new constant. 4 into 3, it will be 12. Now we can apply boundary conditions. In the point A, there is a vertical support. If there is vertical support, there will be no deflection. In the point A, x is 0. So when x is 0, the deflection y will be 0. In this equation, we can apply both of them. So here it will be 0, this one will be 0, this one will be 0. So for C2, we will get 0. The cantilever beam is subjected to point load in the center. In this case, the maximum deflection occurs in the center. If there is maximum deflection, the slope will be 0. At the center, x will be L upon 2. When x is L upon 2, the slope will be 0. In this equation, let us apply both of them. In this way, for C1, we will get this. In the slope and deflection equations, let us apply the values of C2 and C1 so that we will get these two equations. First, let us take the slope equation. We can take W outside and EI on the other side, so it will come in the denominator. Let us keep 16 as LCM. So for the slope, we will get this. Using this one, we can find the slope at any point of the beam. But x will be varies from 0 to L upon 2 on both of the sides. To find the slope in the point A and in the point B, for x we have to apply 0 in this equation. So this term will be 0. In this way, for theta A and theta B, we will get minus WL square upon 16 EI. Now let us take the deflection equation. From these two, we can take W upon 4 EI outside. Finally, we will get this. Let us keep this as equation number 2. And this equation is applicable when x changes from 0 to L upon 2 on both the sides. To find the deflection in the center, that is in the point C. In this equation, instead of x, we have to apply L upon 2 because at C, x is L upon 2. For the deflection in the center, we will get a negative value. That means the deflection occurs downwards. Here you can see the elastic curve. Theta A and theta B will be same, that is WL square upon 16 EI. The deflection in the points A and B will be 0 because there are vertical supports. The maximum deflection will be in the point C, that is WL cube upon 48 EI. Now we are going to end this session. Thank you for watching this video.